Hey everyone, welcome back to the College Algebra playlist. In the previous two videos, we took a look at quadratic equations, right? And we showed that there are two methods you can use to solve them, right? There's factoring and there's completing the square, all right? These methods work, but they're imperfect, all right? They have their issues. With factoring, the problem is that not every trinomial you encounter is going to be factorable over the real numbers. And with completing the square, it's just a long, clunky process, right? It takes a long time and it's difficult. All right. So now we want to ask, is there a nice formula where we can just plug in some numbers and get our answers right away? And the answer is yes, right? That's where the quadratic formula comes in. It's a really nice formula that we can use to solve quadratic equations. All right. So let's dive into it. Okay. Here we go. The first thing we're going to do is derive the quadratic formula. All right, given this equation here, ax squared plus bx plus c equals 0, we're going to complete the square. All right, so we're starting with the problem stated in its general form, right? This is the most general way you can write a quadratic equation. All right, it's in standard form. And we're going to complete the square to find values for x that satisfy this equation. All right, so we start here. All right, and our first step is to divide both sides by a. All right, that gives us this. All right, on the right hand side, right, we just have 0 over a, so that's just 0. Okay, 0 divided by anything is 0. All right, and on the left, this is what we have. All right, we're going to take this c over a to the other side. All right, so we subtract both sides by that, and this is what we get. And at this point, we're ready to determine which number we need to add to both sides to make a perfect square trinomial. All right. So remember, it's this number next to x over 2, whole thing squared. All right. So we're going to take b over a, divide it by 2, and then square that. All right. In the parentheses, this simplifies to b over 2a. All right. And when we square that, we get b squared over 4a squared. All right. That's what we're going to add to both sides. All right. So on the right-hand side, I'm going to swap the order of these two things, right? Well, I'll say b squared over 4a squared minus c over a. Okay, I can do that by the commutative property of addition. All right. So let's get a common denominator down here to make this fraction subtraction happen. All right, I'm going to multiply this fraction by 4a over 4a. All right, let's take this result to the top of the screen. Okay. This times this, right, that's going to give me 4ac over 4a squared. Okay, so we have a common denominator now. We can make this subtraction happen, and we condense these two fractions into one. All right. So at this point, we can factor this left-hand side, right? We can factor this perfect square trinomial. We can factor it as x plus b over 2a, whole thing squared. All right. And then we can take the square root of both sides. All right. And that gives us this. All right. Let's take this result to the top of the screen. This is what we have. All right. So what we're going to do at this step, we're going to split this radical up into two radicals. Okay. On the bottom, I have the square root of 4a squared. All right. That simplifies nicely to 2a. All right. So I almost have what I want, right? I almost have x isolated. I just need to subtract b over 2a from both sides. All right, and that gives me this. All right, and look, we have a common denominator, right? We can write this as one fraction on the right-hand side. And we get this, right? This is the famous quadratic formula. All right? So we can use completing the square to derive this formula. All right? So now that we've seen where it comes from, right, now that we've seen it, let's take it and run with it. All right, let's try to solve some problems by using the quadratic formula. All right, written in standard form, our quadratic equation, right, it looks like this, and any quadratic equation can be solved by using the quadratic formula right here. All right, so any values of a, b, and c, doesn't matter what they are, as long as a is not 0. All right, for any values of a, b, and c, this formula works. All right, it tells you the values for x that you're looking for. All right, so let's try it out. Let's try using the quadratic formula right now. All right, for this problem, I have a equals 2, b equals 7, and c equals 3. Okay? Which means I can plug these values into the quadratic formula to get my solutions right away. All right? Using the quadratic formula is much more straightforward than completing the square. All right? Completing the square is a multi-step process that you have to go through. But with the quadratic formula, right, all you have to do is plug in these numbers and then simplify. Okay? So let's do that right now. Here's the quadratic formula. All right, and I have my numbers color-coded here. All right, we're going to plug in minus b in red. All right, and then say plus or minus the square root of b squared minus 4 times a times c. All right, and that whole thing is over 2 times a. All right. Under the square root, right, this simplifies to 49 minus 24. Okay. Let's take this result to the top of the screen. All right. So under the square root, right, 49 minus 24, that gives us 25. And then in the denominator, right, we have 2 times 2, so that's 4. All right. And look at this. The square root of 25, right, 25 is a perfect square. So we just get negative 7 plus or minus 5 over 4. All right. That gives us two numbers, right? This plus or minus gives us two results. Okay. We get negative 2 over 4 and negative 12 over 4. All right. Those reduce nicely. They reduce down to negative 1/2 and negative 3. All right. So those are my two solutions. Remember, when we solve a quadratic equation, we expect to get two solutions from this plus or minus here. All right. So let's visualize this. Here's what my curve looks like, all right, and it crosses the x-axis at these 2 points. So when we solve this equation here, right, we're finding the x-intercepts. All right, so the values for the x-coordinates of these points are negative 3 and negative 1/2. All right. Let's try one more example. Here we have a equals 1, b equals 1, and c equals 2. Okay? So let's plug those values into the quadratic formula. All right? And this is what we get. Okay? But something interesting happens under the square root. All right, watch this. I have 1 minus 8 under the square root. All right? So I'm going to get a negative number under this square root here. All right? I get minus 1 plus or minus the square root of negative 7, and that whole thing is over 2. All right? This is going to be an imaginary number under the square root here, right? This is going to turn out to be complex. All right? So negative 7, right, I can rewrite that as 7 times negative 1. Okay? And then I can split that into two radicals, right? We've seen this process before. All right? We're just rewriting this as an imaginary number. All right, instead of square root of negative 7, we can write that as square root of 7i. All right, and that gives us two complex numbers. All right, we're writing this in standard form for complex numbers. Something plus or minus something I. All right, these are my solutions. All right, my solutions are complex. So think about what that means. If we were to visualize this solution, right? If we were to visualize the curve, right? This curve, we'll see that the parabola does not cross the x-axis. All right? And that makes sense, right? Because when we solve this equation here, we get complex numbers, right? Involving imaginary numbers. So that means the solutions to this problem, right? They're not real, okay? Because the curve does not cross the x-axis. All right, so this is a really cool application of complex numbers. All right, if you get complex numbers for your solutions to a quadratic equation, then you can say right off the bat, oh, that means that this curve does not cross the x-axis. All right. So let's talk about something else to close the video. All right, let's talk about something called the discriminant. All right, given the problem stated in its general form here, the discriminant is the expression under the radical in the quadratic formula, b squared minus 4ac. All right, the discriminant tells us whether the solutions are real or complex numbers and how many solutions of each type to expect. All right, let's look at this table together. All right, if b squared minus 4ac equals 0, that means that I have one rational solution with a multiplicity of 2. All right, think about what it means for the discriminant to be 0. All right, if the value under the square root is 0 in the quadratic formula, that means that the square root goes away and the plus or minus goes away. And we're just left with one number. All right, and it turns out it's going to be a rational number with a multiplicity of 2. All right, we'll talk about multiplicity in a future video. All right, but for now we just need to know that it's one number, right? It's a double solution. All right, both solutions are just one number. Okay? We expect to get two solutions whenever we solve quadratic equations. But in this special case, right, we just get one number. One rational number, all right? And then if it's positive, all right, if the discriminant is positive and the number is a perfect square, then we get two rational numbers for our solutions. All right? And if it's positive, but it's not a perfect square, all right, we're going to get two irrational numbers for our solutions. All right, they'll involve some ugly radicals. All right. And then, as we discussed earlier, if the number under the square root is negative, that's an imaginary number, right? That's going to be complex, okay? We get two complex numbers for our solutions. All right. So let's look at each of these cases and visualize what happens. All right. Here, I have x squared plus 4x plus 4 equals 0. All right, we're not actually going to solve this equation. We're just going to characterize the solutions. All right, we're going to talk about the solutions on a meta level. All right. The discriminant in this case is equal to 0. All right. So that means that there's one rational solution, all right, with a multiplicity of 2. All right, and what that means graphically is that the parabola doesn't actually cross the x-axis, okay? Instead, it comes down here and kisses it, right? It just touches it at one point, all right? And this makes sense when we think about the trinomial here, all right? This can be factored as x plus 2 times x plus 2, all right? Which means you get x equals negative 2, all right? So when the discriminant is 0, you just get one number for your solution. All right, it's a double root. Okay, let's try another one. All right, here we have 3x squared minus 5x minus 2 equals 0. All right, the discriminant is equal to 49. All right, so 49 is greater than 0. Okay, so we know we're going to get real numbers for our solutions. And 49 is a perfect square. Okay, so that means we're going to get two rational solutions. All right, here's what the curve looks like for this case here. All right. And the other case, when the discriminant is positive, right, is when you have something that's not a perfect square. All right, 28 is not a perfect square. So that means that our solutions are going to be irrational. Okay, we'll have some ugly radicals involved. All right. Here's what this might look like. Okay, it crosses the x-axis in two places, all right, and we know that the x-coordinates of these points are going to be irrational numbers. All right, and then for the final case, this is the most interesting, to me anyway. If the discriminant is negative, right, I get b squared minus 4ac equals negative 31. All right, that means that my solutions are both complex. All right, which means that the graph once again, does not cross the x-axis anywhere. All right? This thing starts below the x-axis and it continues down to negative infinity. All right? And it never crosses the x-axis. So we can use the discriminant to characterize our solutions. All right? We can specify certain characteristics of the solutions. All right? That does it for this video. Thank you for watching, and like and subscribe.